contractually obligated to take a streaming selfie, so if you don't want to be in this, just look down. Sorry. It has to happen. Thank you. So, yes, so glad to be here. My name is Danica Danica, I guess, here. Sorry if I butchered that. I grew up in the US. So excited to be here today to talk about HADR strategies for Apache Kafka. I work for Confluent, which basically our main offering is to make Kafka easier for you, right? We offer fully managed Kafka in the cloud. Okay, so just that little bit of background. So yes, we're going to be talking about HADR strategies, letting you in on a pet peeve of mine. I hate acronyms. I hate abbreviations because there's just a lot of letters that we like to throw around in the technical community. So I'm just going to take a minute and go over some definitions here, all right? Kind of spoiled it just a little bit, but HA, this is high availability, right? So this defines an architectural strategy that will create potentially redundant components across our system with the goal of potentially minimizing or eliminating any sort of downtime that we might have in the event of a failure, right? So the bottom line is that we want our data, our systems to be as consistently available as possible, okay? DR, this is disaster recovery, okay? So in the event of a potentially debilitating disaster scenario, like a cloud outage, you may have encountered one of those, a disaster recovery strategy is going to outline all the steps that need to be taken in order to restore normal business function, right? We want to minimize or even eliminate the upset to our normal business functionality, okay? So high availability, disaster recovery, these are great things. You should want them, want to have a strategy. Hopefully this isn't the first time you've heard these terms, all right? Everyone should have this in the back of their mind when you're building out any sort of architecture. And especially today, right? A lot of us are using cloud infrastructure. It has found a very rightful place in so many architecture diagrams. It's really hard to ignore the effects of cloud outages though, right? On the one hand, there's all these pros to using cloud infrastructure, right? I don't have to manage most of my own infrastructure. It's infrastructure as a service. Someone else is running it, making sure it's live. For Confluent, we make sure your Kafka clusters are up and running. You don't have to think about it, right? You can spin up clusters just a couple minutes. But cloud outages are here to stay, right? Within the past year or so alone, we've had dozens, if not hundreds, of cloud outages that have debilitated a lot of businesses, okay? And the really frustrating thing with a lot of these outages is that when they're occurring, we have very little visibility into what's happening behind the scenes, right? That's the most frustrating part to me, actually, is not knowing what's happening behind the scenes. What actually caused this problem? What steps are being taken to investigate it? What steps are being taken to actually fix it? How long is that going to take? And in the meantime, you're just scrambling, right? Trying to figure out what to do in the meantime. And we're going to continue using cloud infrastructure, right? So we have to learn to live with these outages and have a solid plan in place to work around these. And this is where an HADR plan comes into play, all right? And the good news is that if you're using a technology like Apache Kafka as the sort of central nervous system of your company, you're already starting off on the right foot as far as building out an HADR strategy, okay? So that's what we're going to talk about today. But I really want to make sure everybody knows what Kafka is. How many of you have used Kafka or are using Kafka? Okay, wonderful. Some of you did not raise your hands, so this is for all of us, okay? What is Kafka? The most concise definition that I can come up with is it is a distributed event streaming platform, okay? It's kind of a textbook, very academic definition. Not a lot of words in there, but they pack a lot of meaning. So we're quickly going to just look into these a bit. So it is a streaming platform, first and foremost, okay? That should be a very familiar term to everyone, especially over the last 10 years or so, we've been undergoing a paradigm shift in how we process and deal with our data, right? We're moving away from batch-oriented systems where we wait minutes, hours, days to aggregate our data and then process over it and produce one aggregate result maybe at the end. And we're going from that to stream processing, more of a real-time way of processing our data, okay? So we're going to be producing more frequent results, more incremental results. We're building systems that are more reactive, that deal with the data as it's being created as quickly as possible, almost real time. right? And this is a good thing, right? We want to build more reactive systems, and depending on how you're implementing this streaming aspect in your architecture, you have the opportunity to build a pretty resilient, added more resilient component to your infrastructure. Kafka is also an event platform, though, all right? When you write your data into Kafka, you really ideally should be writing events, okay? And events are just pieces of information that describe things that have happened, okay? So to describe something that has happened, we need a timestamp, all right, pretty easy. And we add some couple bits in there to round out what actually occurred at that moment, right? But the other thing about events, and this is critical to Kafka, is that they're meant to be immutable, okay? So once we've created an event saying that this happened at this time, that's set in stone, okay? We're not gonna change that. It's occurred. I don't have a time machine, right? So Kafka is a platform that allows you to stream data, allows you to move data pretty quickly, almost real time, and it's communicating immutable facts, these events, all right? So the benefit of this is that we can move this information pretty quickly. Consider it's immutable data, right? And then we can also have downstream applications, downstream clients tap into that information pretty quickly, pretty efficiently. So that's more or less the gist of Kafka. We're going to get into the distributed aspect of it in a second. But how does Kafka fit into, how do we use HADR, a solid HADR plan when we're dealing with Kafka? So, like I said, the good news is that using Kafka, it goes really, really well with setting up a high availability disaster recovery strategy. Okay? From the high availability side, we're going to focus on the way that Kafka is architected behind the scene. This really ties into high availability. So, to understand this, we need to go back to some of the basics of storing information in Kafka. All right? So, the primary unit of storage in Kafka is called a Kafka topic. Okay? And these topics typically represent a single data set or individual entity, right? And it's comprised of events. Okay? To get data into Kafka, we write it as key value pairs using a separate client called a producer. We can have as many producers as we want, writing to as many Kafka topics as we want. From there, to get data out of Kafka, we can use another client called a consumer, and we can have as many of these as we want, reading from as many Kafka topics as we want. But there's some additional interesting aspects of consumers. The first thing is that they keep track of where they've left off, right? As they're reading events from a Kafka topic, they keep track of a bookmark, effectively, saying, this is the last event that I read and successfully processed, and I committed this bookmark. And that is stored durably along with the data in Kafka, so that if your consumer goes down at any point in time, when it comes back up, it can continue working and doing what it was doing prior. These consumers are completely decoupled from the producers, okay? Producers don't care about consumers. There don't even need to be any consumers for the producer to keep running, and vice versa. So if the consumers go down for any point, for any reason, the producers are gonna keep writing data to that topic, right? And when the consumers come back up, they'll resume. And the same thing is true of the producers. If they go down, the consumers will still maintain that connection, that subscription to that Kafka topic. They may not receive any events during that time, but they're going to maintain their connection, and when the producers come up, everything goes on their way, right? Consumers also have the ability to work together as a group, something called a consumer group, and in doing so, they're able to share the work of consuming events from a specific topic or a group of topics. So in this way, they're able to parallelize the processing of reading these events from the topic and processing them, okay? And this is a really, consumers can share the work, but then also on the other hand, they're able to work independently, right? They're able to, we can have a group of consumers or individual consumers that are able to read the exact same events from a topic. So they're all going to consume the exact same information, and we can have as many consumers doing that as we want. And this is a really, really important thing in Kafka. So for those of you who did not raise your hand and you're looking to get into Kafka or thinking about it, when you're learning Kafka, it's really easy to compare it to similar technologies, and I feel like messaging queues always come up, right? A Kafka topic is not a message queue, okay? When we consume information from a Kafka topic, it does not go anywhere. It is stored there durably for a configurable amount of time, okay? So during that time, we can have as many consumers as we want reading that information from it. So a Kafka topic is less like a queue and more like a log, all right? So it's more like an application log file. So when you're debugging an application, looking line by line through that log file, trying to determine root cause, as you read that line, it does not go anywhere, right? It's still there. It's durably persisted in that log file until we, roll the log file and maybe have some file cleanup, right? And during that time, before that time, your colleague can come through and read the exact same lines and build up that same state of that application in their minds in the same way, okay? So Kafka topic is a log file. So these topics are actually further broken down. I know I said they were the primary unit of storage, but they're further broken down into additional components called partitions. And these partitions are actually the immutable append-only logs where the individual events are actually stored, okay? And these partitions are then, Kafka's a distributed system, so these partitions are actually distributed on different nodes of the Kafka clusters where they're stored. And this provides better resilience and also opens the door for replication of data, okay? So the nodes of a Kafka cluster are called brokers. These brokers can be running anywhere. They can be bare metal, they can be VMs, containers running in the cloud, wherever you'd like them to run. So this is an example of a simple cluster. We have 3 brokers, we've got 3 topics, 2 or 3 partitions each. So the partitions might be distributed in this way, okay? Results may vary. If you bring up this example, it might be a little different. But this is a toy example, but it still shows you how ideally you would like your partitions to be distributed evenly across your brokers if possible, right? And in doing so, we can get around what happens with broker downtime, right? So on that note, what happens if we just lose it, right? So broker 1 goes down. Already you can see there's some impact here, right? Any producers that we had writing to this particular these partitions, or reading from these partitions, can no longer access that data, right? That data is pretty much gone, all right? The good news is we only lost 1/3 of our data. The bad news is we lost 1/3 of our data, right? But that's better than losing all of your data. Yeah, probably, I don't know. But Kafka takes it a step further with something called replication. So we're looking at a similar cluster setup. We have 3 brokers here, but in this case, we're just looking at a single partition, or single topic with 3 partitions, and we're going to use something called replication. Replication is a configurable parameter that says how many copies of a given partition we want to have across our Kafka cluster, right? So a replication factor of 3 is pretty standard, so that's what you see here. Every partition we have our lead partition, which is the main one that our producers and consumers are interacting with. And then we have our follower partitions, which are the additional copies, the backup copies that we have elsewhere in the cluster. And you'll notice here, so on broker 1, we have partition 0, which is our lead partition. That's the one we're interacting with. And on brokers 2 and 3, we have our follower partitions of that same partition 0. Okay, and ideally, you would want your replicas, your backups, to exist on a different machine as the one that you're interacting with, right? So that in this case, if one of our brokers goes down, right? Okay, so again, we've lost partition 0. That seems pretty bad. We've also lost 2 replicas, 2 followers. The followers, not really important, right? Because we still have 2 other copies of partition 1 and 2 elsewhere, right? The same is true of partition 0, but we only have follower replicas elsewhere. So soon after this broker goes down, the cluster is going to notice that there's no lead replica for partition 0. And it's going to look for a backup, it's going to find that on broker 2, and it's going to promote that follower replica to be the new leader. Everything's going to resume as normal. Our producers and consumers can continue reading and writing using that partition, and we can go on our merry way, right? So in this way, leveraging the partition replication of Kafka, we can sort of ensure that we have more of a highly available cluster, okay? So going back here, Kafka, pretty highly available, right, just in this. We can use multiple brokers, right? We're storing our data across multiple machines, and then we're also synchronously replicating this data to other machines in the cluster, okay? Every time you try to write an event to Kafka, it goes to that lead partition, And from there, it is synchronously replicated to the degree of a replication factor that we have defined to the other brokers where those follower replicas are. Okay, that is a synchronous process. We do not tell the producer it's been written, in most cases, until it's been durably written to all of those brokers. Okay? So within a single Kafka cluster, we can already ensure high availability to a degree, right? That's great. But what if all of our brokers are running in one data center or in one cloud availability zone and we lose it? Okay? Everything's gone. Okay? So we need to take this a step further. We need to ensure that everything is running smoothly in those disaster scenarios. So the best way to get around these disaster scenarios in Kafka is to basically extend your Kafka cluster across multiple geographic regions. Okay? So the durability, the high availability that we saw before within that single cluster, this is going to get better as we extend it across multiple geographic regions. And you're also going to open the door for more, elaborate disaster recovery plans. Okay? Geo-replication is really at the heart of disaster recovery for Apache Kafka. And it's going to provide some of the best RPO and RTO numbers that I've seen. So acronyms, abbreviations, hate them. So RPO, recovery point objective. All right, so this effectively defines the frequency of our data backups, right? How often are we actually replicating and storing backups of this data? It happens synchronously in Kafka if you've defined your replicas properly, right? So in the event that the system goes down, recovery point objective just wants to know how much are we losing. RTO is recovery time objective, all right? So this is how much time we expect to pass between when, right before the system failed and when we eventually fail over to the backup, right? So in any sort of disaster scenario, the ideal situation is that we have an exact copy of everything that we need to keep functioning until we can eventually restore service back to the original data store, right? So in this case, with Kafka, our data is being continuously replicated, right? It's being synchronously replicated every time we write an event to Kafka. So our RPO, our recovery point objective, is going to be pretty low, almost zero, right? Every piece of data is being replicated and copied. Our RTO is just going to be the time it takes to flip the switch and move over to whatever other backup we have, okay? Which hopefully sounds pretty appealing from a disaster recovery standpoint. So from the perspective of Kafka, to achieve geo-replication, all right, all we got to do is spread our cluster across different geographic regions or availability zones, right? That sounds pretty good. How do we do that? So depending on your use case, your individual requirements, there are a couple ways to go about this. The first is just using a single cluster, okay? Pretty much what I described with those initial diagrams with the brokers. Instead of running them within a single data center or within a single availability zone, we're just going to define them across these availability zones and data centers, right? We're still using a single Kafka cluster. All right, so we're going to get all of those benefits that I talked about. That synchronous replication can still occur, all right? We're going to have that durability, that automatic failover and promotion of follower replicas. We'll get that for free. And also, since we're still using a single cluster, our consumer offsets are going to be maintained, right? Having those consumer bookmarks are really, really critical when you have a disaster situation, because when you fail over to your backup situation, you need to know where you've left off in your processing. That's the really critical thing to maintain, right? All right. There are a couple limitations to this approach. Obviously, you'd want to have these clusters in different geographic regions. In the US, it's common to use US West, US East. That's kind of pushing the limits of a single stretched cluster, right? You're adding, 50 milliseconds of latency, which for a synchronous copying over of data, right, you're adding 50 milliseconds every time you're trying to produce data to Kafka. For some use cases, that may be completely fine. For others, that's unacceptable, okay? So you have to really think about what your use case is and whether or not this is reasonable. If you're trying to stretch a cluster across continents, maybe don't do that. You're going to add a lot of latency. This is probably not going to be the best option for you. So to be successful with this, probably stay within the same continent. Don't be too far apart with your availability zones or your data centers. And you need to be able to maintain a low, stable latency and a high bandwidth connection, right? To get around these limitations, Confluent offers a different type of broker called an observer, which basically just does asynchronous replication. So we have the synchronous replication that happens anyway by default in Kafka, but then we have these additional broker nodes that are able to eventually request that data is copied to them, right? And that happens asynchronously. It's not going to impact the normal production of your data, and your data will eventually just be replicated over to different nodes. All right, so that may be something to look into. In addition, when you're setting up a stretched cluster, there's a little bit of overhead. You have to pay attention to where your replicas live, right? Because you don't want to have all of your data copies still within the same data center or availability zone. So Kafka, thankfully, has the ability to be rack aware. So when you set up your brokers in one availability zone and the other, you can define the rack that those operate in, and Kafka will balance the replicas accordingly. Okay. So if that sounds like a little too much overhead, too much work, maybe a multi-cluster setup is going to be more appealing to you. So in this case, you're setting up fully standalone clusters in different availability zones, and you're going to have a separate third process actually do the replication for you. Okay. How you go about this can vary, but before we get into that, I want to touch on some of the use cases that for multi-cluster setups, okay? I know we're talking about this mostly from a disaster recovery standpoint, but there are other interesting use cases where you might want to set up different clusters and have this replication process operating. So the first is an active-passive setup. This is basically what we've just been discussing, right? We have one cluster that is our main cluster. We're producing to that. We're definitely consuming from that. And we want to have a passive cluster that we are just replicating this data over to. We can be consuming from that passive cluster, but we definitely don't want to be writing any data into it, okay? This is good for any sort of backup scenarios, DR scenarios, also regulatory compliance for a lot of industries need a setup like this. Active-active, as it sounds like, we're going to have two active clusters here, both of which have data being produced into it. We may have separate sets of consumers there. So in this situation, maybe you have separate clusters. You're a global business. You have clusters operating on different continents. You don't really want to replicate that data synchronously, but you do want to have that data to be eventually consistent and available on all of your clusters. So in this case, we have replication going both ways, right? We need to copy it from the one cluster over to the other and from that one back to the other one. This can introduce some cycles. So thankfully, the tools we're going to talk about do have ways to resolve this and avoid those cycles. So it's just something to keep in mind when you set it up. We have fan-in, okay? So this is where we have a number of smaller Kafka clusters that are active. We are producing to these, and we're replicating that data over to a single larger aggregate cluster. Maybe for some larger processing jobs, we want to have that data available in a single cluster. This can be used in like IoT use cases where maybe we have clusters operating at the edge. There's not very good connectivity, but eventually when it has the right connectivity, it's going to copy that data over to the centralized cluster. And then we have fan out, which is effectively just the opposite of this, right? We have our centralized cluster where we're mostly producing to, and then we have maybe some smaller clusters that we are replicating either all or maybe a subset of that data to. This is actually another option for DR strategies, right? Instead of having a single cluster that we are using as a backup, maybe you want 2 or 3, right? Have some additional data stores. This is also useful where we have a central cluster where you're doing most of your data processing, and then maybe you need smaller clusters closer to your clients, closer to the applications that need this data, right? So that there's lower latency when those clients go to request that data later on. So these are some of the options you have, some interesting use cases for replicating data to Kafka clusters. So what are our options for actually conducting the replication? The first is using something called Kafka Connect, all right? So Kafka Connect is just a way to connect data sources, data sinks with Kafka, okay? So using Connect, we define a connector that basically just says, this is how I connect to the source and grab the data to pull it into Kafka. And if data is in Kafka, this is how I connect to the sink and move that data out, okay? Common use cases are, if you have data that's continuously being written to a database, and you need that update present in Kafka for some stream processing later. You will set up a connector to periodically pull that database and translate that information, those updates, into events that can then be joined on your streaming data later on. You can also do it the sync direction by, after you've done your stream processing, maybe you want to move your data out of Kafka for long-term storage. So you can use a sync connector to move it into S3. All right. Depending on your Kafka distribution, what you use for your Connect-based replication is going to change. If you're using vanilla Apache Kafka, you'll use something called Mirror Maker 2. For a Confluent distribution, you'll use Confluent Replicator. They're both Kafka Connect-based. They're going to bridge this gap and do the replication from one cluster to another. So again, consumers keep track of their offsets. So when we move over to a backup cluster, we need to know what our offsets are, right? Because again, that's the most important thing, is being able to resume our processing. Both Replicator and Mirror Maker 2 have ways to translate these offsets so that when you do flip the switch and fail over, your consumers know which offset they should be picking back up from. It's going to be different though, right? Because when the offsets are translated over, you're at a completely different space in the storage of that data. So there is going to be a different offset existing on that destination cluster. So Mirror Maker 2 and Confluent Replicator, great tools, Connect-based, to help you replicate your data between clusters. The only downside is that you have to maintain a separate Kafka Connect cluster to make this happen. So if that's not appealing, then your other option is to use something called cluster linking. So this is available, this is something built into Confluent brokers. All right, so what it does is it copies the data from the source cluster to the destination cluster byte for byte. Okay, so it mirrors those into mirror topics on the destination, but it also mirrors topic configurations, topic structure, your ACLs, and your consumer offsets. Okay, all of that is going to be mirrored over to the destination. Okay. Unlike Mirror Maker and Replicator, this is built in, right? So you don't have any additional infrastructure to maintain. Other cool features, like I said, is the byte for byte replication. You're going to maintain your consumer offsets. There's no translation that needs to occur. So as soon as you flip the switch and promote that destination cluster as the new source, your consumers can resume like nothing happened. The mirror topics on the destination are also read-only. So you're protecting the integrity of that data, and you know that it's going to be the exact data you need to function when you do flip that switch. You're going to get your full access control lists available, so you know everyone that needs that access to that data is going to have it. And the whole thing, this is the best part, I know we're running out of time, is you can control at the topic level what data you're actually copying over. So for companies that have very specific business units that have data that definitely needs to be copied, but maybe there are other business units that you don't need to, you don't want to waste time paying for or migrating that over. You can control that at the topic level. And, all right, here's a QR code. Keep going, because I've run out of time. Check this out if you're interested in looking at some more multi-cluster setups. They're pretty fascinating. And I'll put this back up. But anyway, I know it's lunchtime. We have no time for questions, but I will be around, and we can chat.
We can take a few.
Awesome. Okay, I've been given extra time.
Yeah.
Nice.